So this is 8.3. We're now talking about confidence intervals for means. Last section was for proportions. This section is all about means, x bars and mu. So let's first talk about the activity, the one with the farmer's tomatoes. It says, how did the two methods compare? Did one method do a better job of capturing the true mean, and why? And one method definitely did do a better job than the other. So for starters, when we use sigma, which was the population standard deviation, with z star, right, with just a z-score from the normal distribution, that actually captured mu. And by that I mean when we made our 99% confidence interval, the whole 99% bit was true. So I've actually got the applet pulled up here, and we're going to just quickly illustrate. If I use z-scores, so z with sigma, which is the population standard deviation, and I'm going to do 50 at a time, you'll notice these intervals are actually really accurate. I keep clicking. Okay, I see some red in there, but in general, look at the capture rate. It's 99%. What do you know? So we're doing, I've already done 1,000 and I'm at 99%. So this actually works if we can use z-scores with sigma, which is the population standard deviation. But notice, we've got that fixed at 40. That's not changing. So that's actually important here. Because for these intervals, the ones that were actually accurate, sigma is just a constant. It's just 40. And it stands for the population standard deviation. And those intervals that we saw were actually built on a sample mean, x bar, as the point estimate, plus or minus the z-star critical value times sigma over the square root of n. And that's the population standard deviation over the square root of the sample size. So it turns out this one worked really well. The one that didn't work so well was when we used s instead of sigma. So if we use s, that's lowercase, stands for the sample standard deviation, with our z-star, that actually was not accurate. So let's take a look at the applet again. And I'm going to change this from being z-star with a sigma, right, to z-star with s. So instead of the population standard deviation, now we're going to use the sample standard deviation, which will be different from sample to sample. So I'm going to get 50 at a time. Here we go. There's 50, 50, 50. Remember, the claim was 99% confidence, but we're actually getting a lot more misses than that in each group of 50 here. And another thing you should notice is the widths of these intervals are different from one to the next. So it's not a fixed constant like we saw in the first case. So we can say because s, lowercase s, allows for sampling variability, which means it's different for each sample. So we're not getting a consistent capture rate anymore. It's not really 99%, which is a shame. So in the first case we had this guy, that one actually was good. The second case, everything was the same except for we didn't use sigma, we used s. So we still used x bar for the point estimate. We still used a z-score for our critical value. But instead of the population standard deviation, we had to use the sample standard deviation for each interval. So we used little s. And it turns out that one is not accurate. That one's no good, right? And why is that? Well, for one, we get different results every time. For two, there's sampling variability going on, right? They could have large intervals or small intervals, which means our 99% isn't going to be consistent. Right? We saw we only had 93% as our capture rate. Okay, so we need a way to fix this, because most of the time, we're not going to know what the population standard deviation is. We're only going to have our sample standard deviation. But apparently it won't work if we just use a z-star value. So our method is not a z-score, but in fact a t-score of sorts. So there's a t-star critical value. When should we use it over a z-star critical value? And this is actually exactly what we just illustrated with the applet. We want to use it when we're using s, little s, the sample standard deviation, as our estimate for sigma. We'd like to know sigma, but too bad, we don't. We have to use s instead. That's when we have to use t-star. So in other words, when sigma is unknown. And I want to be really clear here, these are for population means, right? These are for population means only. That's what this section 8.3 is about. So if we're actually given sigma, which would be really rare and impractical, because if we already knew sigma, we would probably already know the true population mean, so there'd be no inference for us to do as statisticians. But that would be the only time you would actually use a z-star. But for all practical purposes, when we're trying to estimate a population mean, we're making these confidence intervals, we're going to actually use these t-star values. So z-stars came from the normal distribution. We actually have a new distribution for the t-stars. Actually, it's just called a t-distribution. So I want to show you something from our textbook that compares the t-distribution to the standard normal curve. So the t-distribution itself actually depends on sample size. So the purple curve here, this is actually the standard normal curve that we're used to. And then the red curve, the dotted one here, would be the t-distribution with 2 degrees of freedom. And we'll talk about that in a second. That means it's got a small sample size. And then the light blue one here, that's a t-distribution with 9 degrees of freedom. So it looks really similar to the normal curve, except you'll notice that the t-distributions are shorter and they have more area out here in the tails, right? So they're above the normal distribution out here. But otherwise, the shape of this thing is very similar to the normal distribution. So we learned last section how to get the z-star values out of the normal curve. How the heck do we get our t-star values, right, like a t-score, from this distribution? Well, it's similar. It's similar to the normal distribution. We're going to look for tail probabilities. So what's the tail probability that goes with a given confidence level, whether it's 95% or 99% or what have you? An example of the tail probability, if we want a 90% confidence level, well, that means there's 5% left in each tail. And we can use a chart, which you get on the AP exam and our exams, or you can use your calculator. Just like we had inverse norm, there's an inverse t command. And if you want to take a look at a t-chart right now, it's table B in the back of your textbook. It comes right after the normal distribution table. Okay, in the degrees of freedom piece, I told you that had something to do with sample size. It's actually a really easy formula. We abbreviate degrees of freedom to just be df. And how do you know what it is? Well, it's just n minus 1, sample size minus 1. So like how I told you before, the curve that was only 2 degrees of freedom, that must have been a really small sample, meaning the sample size must have just been 3. So we're going to come back to this degrees of freedom piece and the tail probability part when we take a look at the t-chart and how you read t-star values from it. But for now, let's talk more about the t-distribution itself, right? We've already looked at the graph. Let's talk about the shape, center, and spread of the t-distributions. And notice that's plural because there's different distributions based on the degrees of freedom, which depends on the sample size. So the shape, it looks a lot like the normal curve in the fact that it's symmetric, it's unimodal, meaning it just has one hill, right? But it's not quite the normal curve. So what exactly is different about it as far as the shape's concerned? Well, we say it has fatter tails. And this is the part that helps correct the sample standard deviation thing we talked about in the beginning of the notes. So why does it have fatter tails? Well, that allows for more variability away from the middle or away from the mean. So the values aren't quite as stacked up around the mean, right? They're more spread out. And if we go back to the graph here for a moment, we can see that the purple one, that's the standard normal curve, so it's taller and skinnier. And our two examples for t-distributions are shorter and they have fatter tails. So they allow for more sampling variability. They're not as stacked up on the mean as the normal curve is. And then for the center, well, you notice they were the same for both curves, right? The center, they're both at 0. Why is that? So the mean's equal to 0, just like the normal curve. Well, because t is a standardized score, just like z-score was a standardized score. And if you remember the z-score formula, we subtract the mean, divide by the standard deviation. That turns everything into a standardized score. So the distribution itself is centered at 0. And as for the spread, we know it's greater, right? It has greater spread than the standard normal curve. We saw that in the graph, right? And that refers to the thing having heavier tails. Okay, so let's see if we can get one of these t-star critical values in the first example here. It says, suppose you wanted to construct a 90% confidence interval. You're going to try to capture the true mean mu of a population based on an SRS of size 10. So our sample size is 10. What critical value, t-star, should you use? Okay, so if we're using t's at all, the first thing we have to mention is the degrees of freedom that we're going to use. So in this case, degrees of freedom would be, well, 10 minus 1, so 9 degrees of freedom. All right, so let's take a look at this t-chart. And remember, there's one in the back of your book. It's table B. So the chart itself is actually organized, if I can zoom in here, by degrees of freedom. So if you use degrees of freedom of 1, 2, 3, 4, 5, and so on. And then you can align that with the tail probability. So for our example, we're using 9 degrees of freedom. So I'm going to find 9 under degrees of freedom, and we're at 90% for our confidence level. So our tail probability in this case, if 90% is in the middle of the curve, that means we've got 5% in each tail. So I'm going to see where this aligns. 5% and 9 degrees of freedom. Looks like we're at 1.833 for our t-star value. So our answer, t-star, is 1.833, which we got from the table. And in general, I think the t distribution, that table is easier for kids to use than the normal distribution. All you have to do is find the degrees of freedom you want, right, which depends on your sample size, and then match that with the tail probability, and you're good. You have your t-star critical value. So part B says, what if you wanted to construct a 99% confidence interval for mu, and you have a sample size of 75? So that's definitely going to change our degrees of freedom. And remember, when we're talking about the t distribution, we have to say what the degrees of freedom are. So in this case, it's 74. So let's take a look at the chart. So here's my degrees of freedom. I'm going to scroll down because we said 74, right? And this is the same chart you get on the AP exam or the exams in class. And you'll notice, let me zoom in here, the degrees of freedom column, hello, it looks like they skipped 74 somewhere here. So degrees of freedom, they stopped counting by ones at some point. And you'll notice I have either 60 or 80. I don't have 74 in here. So we have to make a choice as to which one we should use. And in all cases like that, if you don't have it, right, the degrees of freedom is too large, like 74 is too large, you should make the conservative choice. Make the conservative choice between 60 and 80. And in this case, the conservative choice would be the smaller number because degrees of freedom depends on sample size. So you've always got to actually round down and be conservative. You can't pretend that you had a bigger sample than you did, right? If we picked 80, that's like pretending we sampled 81 people, which is hopeful but not fair. So in this case, we have to be conservative and we have to use 60 as our degrees of freedom. We can't just round up. We can't pretend that we have better data than we do. So what's the answer we get if we use 60 for our degrees of freedom? So here's the chart again. Here's degrees of freedom 60. Now, I don't know, I can't remember which column is 90%. I don't want to scroll up. But it turns out, if you look at the bottom of this chart, there we go. Let me just zoom out a little bit here. If you look at the bottom of the chart, it tells you which confidence level goes with which column. So maybe that's even better than the tail probability piece at the top of the chart. So we know we want 99% confidence. Let's just map that out with our degrees of freedom, which is 60, and it looks like our t-star is 2.660. So this is useful as well. You can just align it with the appropriate confidence level. So all of a sudden, this table is looking a whole lot easier to use than the normal distribution table. But I prefer the calculator anyway, so let's talk about that. Without the calculator, we're looking at t-star is 2.660, right? Okay, let's see what we would get if we use the calculator. And it's really similar to the normal one, except instead of inverse norm, we're going to use the command inverse t. So INV-T. And all your calculator wants to know is, what's the area, which is area underneath the boundary mark, and what's the degrees of freedom? So the area component, that's the same as the normal inverse norm command. So for a 99% confidence interval, the area you could use is either 0.005 or 0.995. Either one will work. In this case, I'm going to use 0.995 so I can get the positive answer. And degrees of freedom is 74, so we input that in our calculator. And that actually gives us our t-star of 2.644. Notice they're close, right? The calculator one is a little bit better in this case, but you can actually use either one because you'll have the table available to you on the test. Okay, then the last piece for these notes is, what are the three conditions for constructing a confidence interval for a population mean? And remember, that's mu, right? So the population mean is mu, and we build this interval based on our sample mean. So that's our point estimate, and then we build the confidence interval off that. We're trying to capture mu. Okay, so that's just a reminder. The conditions you'll recognize from last section. Last section was all about p-hats and proportions. This one's all about means. So the first one, let's get the easy stuff out of the way. That's randomness. So the survey that's done or the experiment that was done, we can't trust it unless it was done randomly. And typically that's just mentioned in the problem. So we can just state, hey, the problem said it was randomly conducted, so that condition's good. Check mark. The next condition, how about independence? So if we're sampling without replacement, the 10% condition got us there. So for independence, we usually mention the 10% condition. And lastly, we have something about normality, right? I'm going to put it in quotes here because we're not using the actual normal distribution, but we still want to meet this normality condition, right? We're going to use the t distribution at the end of the day. So if you remember back to chapter 7, the way we made sample means become normal, right? The sampling distribution, that is, well, there's one way we could have a large enough sample. So if n was at least 30, the central limit theorem said normality was all good. So if you got a big enough sample, check mark, you're all good. What about in the sad scenario when you have a small sample though? So sample size is less than 30. Okay, so hopefully the data just automatically came from a normal parent population. But a lot of times we don't know the actual shape of the parent population. So we're going to have to make some assumptions. And to be safe with those assumptions, sometimes we're given a graph of the sample data. So even if it's a small sample size, it's still easy to make a graph of it. So if we're given a graph of the sample data, and it doesn't look overly offensive, and by that I mean you might consider it symmetric and there's no outliers on the graph, then we'll just go ahead and assume that the data came from a normal parent graph, so that the parent population was normal. So as long as there's not any crazy outliers and we have the sample data, we're looking at it, it's safe to assume that the data came from a normal parent population. So for a really rough example, and you don't have to draw this in your notes because you probably don't have room at this point, but let's say you have a sample size of 10, and this is what a graph of the sample data looks like, right? So there's nothing too offensive here, there's no outliers, and it's vaguely symmetric. So this we could say, okay, we'll go ahead and assume that this data came from a normal parent population. So at that point, we've met all three conditions, and we can use T procedures when we make our interval. So I want to end these notes by going back to that applet and seeing what happens when we use a t-score. So I've got the applet pulled up here. I'm just going to change, I'm not using z-scores with S. We found out that was no good. Let's change this to the t distribution. I'm going to reset it here. We're going to do 50 at a time. And notice, yeah, we're missing here and there, but we're at a 99% capture rate. So right now I'm at 99.1%. So we talked about the t-distribution and what it does as far as helping us build confidence intervals and make inferences for means. We talked about our t-star critical value. We talked about degrees of freedom and the characteristics of the t-distribution. So that is all for these notes. I'll see you in class.